Lattice Structure Optimization creates blended solid and lattice structures suitable for 3D printing. The solution is streamlined through two optimization phases from concept to detailed final design. The first phase is similar to regular topology optimization, except in the end, the intermediate densities are converted into an explicit lattice structure. In the second phase, the lattice member dimensions are size optimized. This live demonstration will show a two-stage lattice optimization process from concept to fine-tuning phase and reviewing the results. The design space is a frame component mesh with hexahedral elements. The design variables in the first stage are densities of each solid element, and in the second stage radii of lattice beam elements. The weight of the frame is constrained to be below 0.8 kilograms. The first phase stress should be below 0.5 GPa and the second stage stress below 1 GPa. The objective is to minimize weighted compliance, which is maximizing the stiffness. One plane symmetry pattern grouping is used, which automatically activates minimum member size manufacturing constraint. The units are in kilogram, millimeter, kilonewton, gigapascal, and the linear elastic material is titanium. 4 load cases are adapted from a 2008 research paper by Maestrelli and Falsini. Porosity controls the amount of intermediate densities in the model in the first phase of lattice structure optimization run. This is similar to the penalty applied during a regular topology optimization. There are 4 lattice types available for hexahedral elements and 1 each for tetrahedron, pentahedron and pyramid. Traditional manufacturing methods cannot manufacture medium-dense elements, so in topology optimization, discrete designs are enforced by penalizing medium-dense elements. In lattice structure optimization, medium-dense elements are allowed because 3D printing or additive layer manufacturing can manufacture lattice structures. A lattice is a beam microstructure which is porous, meaning in between solid and void. The lattice beam elements have the property PBML and type rod is automatically assigned for each element. The thickness of this tapered beam element can vary along its length and only circular cross-sections are available. Let's begin by choosing the OptiStruct user profile. Next, we'll import the solver deck. Choose Demo Bicycle Frame.fen. Turn on the shaded visualization. Review the beam section collector. We see that the radius is 10 millimeters. Review the frame component. There are 4 load steps: the bump, brake, standing and sitting. The material properties are 150 GPa, the Poisson ratio is 0.35. Here are the beam and the solid properties. Now the optimization will be set up. Go to Analysis, Optimization, Topology. Then define the desvar, in this case lattice. Check the P-Solid property selector and select the frame component and click Create. Then on the Parameters subpanel, enter stress constraint as 0.5 GPa and hit Update. We'll also define a one-plane symmetry on the pattern grouping panel. Choose the anchor and the first node accordingly, so the symmetry plane will be in the XZ direction. and click Update. Now we're ready to set up lattice-specific options. The lattice structures are constructed using 1D tapered beam elements. Two types of lattice cell layout are available: tetrahedron and pyramid, derived from tetrahedral and hexahedral meshes respectively. The lattice cell size is directly related to the mesh size in the model. For lattice type, choose one. Lower bound and upper bound fields can be used to specify the range of densities for elements that can be converted into lattice cells. Elements with densities above upper bound remain as solid elements, and those with densities lower than lower bound are removed from the model. The intermediate density solid elements that lie within the density bounds are replaced by lattice structures. Set lower bound to 0.01. The stress value field on lattice continuation line can be used to specify the stress constraint for the second phase. If stress is critical constraint for the design, user should define slightly lower value of stress constraint for phase 1 in the topology panel, so that in the phase 2 the solver will achieve a feasible solution with the actual stress constraint defined in the lattice panel. Then go to Edit Lat Parameter. The beam cleaning procedure occurs at the end of the second optimization phase to remove beams with very low radii. Beam cleaning can be controlled with clean. In this case, no cleaning will be used, as removing beams might increase stress, which is critical to this design. LatLB can be used to verify or automatically set lower bound value. This process aims at generating a model that allows for maximum beam element removal and at the same time retaining reasonable model compliance performance. Porosity defined as low will lead to a final design with mostly fully dense material distribution, and is appropriate if compliance minimization for a given target volume is required. The amount of intermediate densities in a model depends primarily on the penalty applied. This is similar to the penalty applied during a topology optimization. In the optimization view, we can see the newly created cards and review them in the entity browser. Remember the DRCO approach? We'll use it now. Since we already defined the design variables, we need to continue with responses. The first response we're going to create is mesh response. Set the property type by entity and select the property. In this case, we need to select the property type as P-solid and select the frame component. We'll create the weighted compliance response. Here we need to choose the load steps. We can also define weight for each individual load case. Now we need to define the constraints. Let's set up a mesh constraint. With the upper bound of 0.8 kilograms. Finally, we set up the objective, which in this case is minimize weighted compliance. Now that our optimization formulation is complete, we can go ahead and run the optimization. While the optimization is running, we can click on Graph and review how the objective function is evolving through the iterations as well as maximum constraint violations and maximum displacements for each subcase. Also, we can look into the output file. We can see the active constraints for each iteration as well as compliance. Now that the optimization has finished and it is converged, meaning that a feasible design is found, let's again open the output file. Here we see the lattice optimization parameters. Because we set up one plane symmetry, the minimum dimension member was automatically set up. Let's scroll down to the end and review the lattice lower bound check, which is turned on by LatLB parameter. In this case, it was adjusted automatically. 3,000 solid elements with low densities were removed and 34,000 lattice beam elements were created. Let's review the result. We can review the evolution of density throughout optimization iterations. Use the ISO contour plot to isolate only elements above certain threshold. Next, we'll import the solver deck from the first phase. At the end of the first phase, a new file with the lattice suffix is generated. This new file includes the 1D element data, which represent the new lattice structure and the sizing optimization setup. You have to redefine the optimization responses, constraints, and the objective function. Here is a warning that unsupported card was imported. And we can see that in the OptiStruct lat param card, it was inserted automatically. Also, OptiStruct OptiControl card was defined initial fractional move limit for size. A single design variable is automatically created for each joint of lattice tapered beam elements, representing the radius of all the beam cross sections at a joint. The design variables are related to the radii of each tapered beam element by design variable property relationship entries developed in the size optimization process. Let's first hide the add-on components to isolate only the frame. In the tool Mass Calc, we can calculate the weight of the frame. Let's run another analysis to compare to the first phase optimization results. Meanwhile, we can already go ahead and modify the optimization formulation for the second phase. We'll change the mass response to total . And we need to define the list of properties of the stress response. Because now our mass constraint will include also add-on components, we need to calculate the weight of those components. Let's use this number and add to it the frame weight. We can see that the upper bound stress limit was already propagated from the first phase optimization formulation. We can choose on the stress response the normal, shear or von Mises stress. Now that the analysis which ran in the background is complete, we can compare it to the optimization run. Note that the displacement are slightly off. But don't worry, because we're going to improve those in the second phase. Let's open up the animation result. Go to Result, Scalars, C-bar C-beam stress, and set Model Animation Type. We can see that the bump load case exceeds our 1 GPa stress limit. Other load cases seems to be fine. Let's see how 1D detailed beam representation looks like up close. We can see that the beams are functionally graded. Where most stresses occurs, we have thicker beams at the junctions. Now we can run the second phase optimization, which will take a while. Now that the second phase has converged, let's review the graph. We can see that all the displacements improved and the maximum constraint violation is minimal. Also, the objective is greatly reduced. Let's compare the result of the second optimization phase to the first optimization phase. The objective has still improved. Let's import the optimized solver deck. And perform analysis. Final analysis matches exactly the results from the optimization run in the second stage. Open up the animation results. And set the model animation type. Let's review the C-bar C-beam stresses and observe that the bump is now inside the limit. Also, all the other cases seem to be okay. A simple design of experiments was run to explore the trade-off between stiffness and weight. 4 separate optimization runs were performed, each with its own weight constraint, and the resulting stiffness was extracted. Plotting the stiffness versus weight enables the designer to identify the point of diminishing returns. In this case, increasing the weight beyond 0.8 kilograms does not increase the stiffness at the same rate. This concludes the presentation. Thanks for watching.